Venus. Often referred to as Earth's hellish twin sister, the history of observing and exploring Venus goes back almost as far as that of Mars, but with a little less effort put in. It's a lot harder both to reach Venus and to study it. It's blanketed in thick clouds and has a crushingly high atmospheric pressure. For many, Venus is a very mysterious place, and while there hasn't been quite as many missions sent to it as there have been to Mars, there is a surprising amount to say about the exploration of Venus. Let's begin, as they say, at the beginning. Like the other four major planets, those being Mars, Jupiter, and Saturn, Venus has been known about since prehistoric times. However, because it is closer to the Sun than the Earth, Venus is only visible either early in the morning or early in the night, giving it the nicknames of the morning star and the evening star. Early cultures, such as ancient Egypt, regarded these as two separate objects. Venus's position in the solar system would cause it to disappear for days at a time, then reappear on the opposite horizon, making it difficult to actually connect these two appearances without doing a bit of math. Even the ancient Greeks made this mistake until the Hellenistic period, naming the two stars Bringer of Light and Bringer of Dawn. After realizing it was a single planet, it gained its modern Greek name of Aphrodite. The Sumerians in around 3000 BCE named the planet after the goddess Inanna, who represented love, fertility, and war. The Maya based their entire religious calendar around the movements of Venus, going so far as to time wars and other events around its appearance. They were capable of charting its synodic period, basically its path across the sky, to within 1/100th of a day. In the 1600s, telescopes came around, and we began to make clearer observations of the planet. Unlike Mars and the other outer planets, Venus exhibits significant changes in phase from our perspective, which Galileo was able to observe between 1610 and 1611. Though it was still contentious at the time, his observations seemed to match with Copernicus's heliocentric model, as it appeared to get smaller as its phase waxed and got larger as it waned. This indicated the planet would be at its smallest when it was in a full phase, but we could never see when that happened, with Galileo concluding it was behind the Sun at the time. None of these observations make very much sense in a geocentric reference system. In 1639, the first transit of Venus in front of the Sun was recorded by astronomer Jeremiah Horrocks and his correspondent William Crabtree. Assisted by the new astronomy of Johannes Kepler, which assumed orbits to be elliptical rather than perfectly circular, the two self-taught astronomers made separate observations of the transit on December 4th, after correctly predicting a transit of Mercury in the previous year that was unseen even by Kepler himself. This transit allowed Horrocks to develop a helioscope, which is sort of like a primitive solar filter. It uses a telescope to project an image of the Sun onto a piece of paper in a darkened room, protecting the eyesight of the observer. Over a century later, in 1761, Russian polymath Mikhail Lomonosov observed another transit, and by this time, telescope technology had improved enough that he could see a luminous arc around the planet, confirming the previous assertion that Venus had an atmosphere. By the 19th century, Giovanni Schiaparelli made a significant observation and assertion about Venus. He said it was tidally locked to the Sun, meaning its rotation matches its orbital period, causing one side to always face the Sun. Previous astronomers believed it to have a rotation period of around 24 hours, similar to Earth, but Schiaparelli's belief was closer to the truth, if still incorrect. Venus's rotation has a near resonance with its closest approach to Earth, meaning that when it gets close, it is almost always facing the same direction, though not perfectly. In reality, Venus rotates once every 243 Earth days. Does anyone remember the alleged canals on Mars that were long believed to exist, but wound up being simple telescope artifacts? Well, it happened again with Venus, with the same astronomer. In 1896, Percival Lowell used a new 24-inch refracting telescope and began to make observations of Venus. When he stopped down the aperture of the telescope, he began to notice something strange. At this point in time, it was well known that the surface of Venus was completely obscured by thick cloud cover. However, he still maintained that he could see a dark spot on the planet's surface with numerous straight spoke-like structures jutting out from it. Even stranger, the structure was always there, leading him to believe that Venus must be tidally locked to the Sun. His findings were derided by virtually everyone. No one else could see the structures, and none of it matched what was known about Venus at the time. It was left unsolved for an entire century, until finally, a few amateur astronomers came up with a working theory. Percival Lowell had been looking into his own eyeball. Lowell tended to observe Venus high in the daytime sky. With his lens so stopped down in diameter, he had shrank the telescope's exit pupil in front of his eye to a pinhole. He had effectively turned the telescope into a giant ophthalmoscope, an instrument used by optometrists to examine their patients' eyes. Andrew T. Young of San Diego University explained the phenomenon, saying, quote, "As the eye pupil moves with respect of the small telescope pinhole, the angle at which rays arrive at the retina changes so that features that are within the eye but a little removed from the retina may cast shifting shadows on the latter and be seen." Percival Lowell had been staring at and mapping out his own retinas onto the surface of Venus. Speculation as to the nature of Venus's surface was abound prior to direct radio observations in the early 1960s. Its size, orbital radius, and thick cloud cover led many to believe that it had a lush, Earth-like environment and possibly even had dense jungles. The fact that its surface is completely hidden from the naked eye was very helpful to science fiction writers whose minds were allowed to run wild about its nature, speculating about alien life adapted to hot, dense environments and imagining the nature of what an alien jungle might look like. It wouldn't be until the 20th century that microwave observations and spectroscopic analysis would reveal the incredibly high surface temperatures of up to 465 degrees Celsius or 870 degrees Fahrenheit. Venus was the second object in the solar system to have radar mapping done of it, the first being, well, the Moon. I mean, what did you expect? In 1961, NASA's Goldstone Observatory and the National Astronomy and Ionosphere Center in Arecibo carried out the first radar explorations of Venus. We were now able to confirm two things: the 243-day rotation period and the direction of rotation. Venus is unique for our solar system in that it rotates in the opposite direction from other planets. Sort of. In reality, its axial tilt is almost 180 degrees. Essentially, it's upside down compared to other planets. So it's rotating in the same direction, but because of the extreme axial tilt, it looks like it's going the other way. Later radar experiments also managed to confirm the radius of the planet, 6,052 kilometers or 3,761 miles. Previous estimates using ground-based telescopes were off by a factor of 70 kilometers, possibly due to the planet's incredibly thick atmosphere. By this time, the space race had begun, and it was time to get up close and personal with our nearest intercelestial neighbor. Before we go into it, I have a few points of order to discuss. First, I will be touching on every Venus mission in order, including those that failed to reach Earth orbit. Second, I will not be including missions that flew by Venus but did not feature it as their primary mission. This will exclude exactly 6 missions, those being Galileo, Cassini, Messenger, the Parker Solar Probe, Bepi-Colombo, and the ESA Solar Orbiter. Third, let's take a moment and discuss why Venus is actually harder to get to, in a way, than Mars is. First, we need to talk about transfer orbits. Because Mars is further away from the Sun than Earth, a spacecraft on a Mars intercept course is headed toward its apoapsis, or the high point of its orbit. This means it is actively slowing down as it heads to Mars, and therefore, once it reaches Mars, doesn't have as much velocity to kill as it does when it's in the other direction. While it requires less delta V, a change in the rocket's velocity, to get on course toward Mars rather than Venus, it requires almost twice as much delta V to then get into orbit of Venus, because at this point it's headed toward periapsis and therefore gaining speed. You have a lot more velocity to bleed off to get into orbit of Venus, and it is for this reason that Mercury is barely explored at all. That and the whole being cooked by the sun thing. Next, you have the problem of the nature of Venus itself. While Mars has its own obstacles to overcome, low temperatures, thin atmosphere, dust storms, Venus is a much more hostile and volatile environment. Spacecraft that enter the atmosphere have to withstand incredible, crushing atmospheric pressure, comparable to being about 3,000 feet below the surface of the ocean on Earth. The temperatures, as we've established, swing in the opposite direction of extremely hot, which doesn't taper off at night. Venus has a perpetual greenhouse effect from its thick atmosphere, and the day and night are virtually the same temperature. A spacecraft on Venus gets no respite. Between the temperatures, the pressure, and the clouds of corrosive acid, nothing that gets there is destined to last for very long. The order of the day is to build sturdy, build fortified, and expedite data gathering to get as much information as possible before everything melts and/or is crushed under the weight of that yellow hellscape. So, with all of that being said, let's dive into the list of spacecraft that explored Venus. Let's start with a extensive list of the first failed Soviet attempts. Between 1961 and 1984, the Soviet space program developed a battery of interplanetary probes for their Venera program, which means, wait for it, Venus. Really creative with those program names, the Reds. The program would set a number of precedents over the course of its life, including what is often touted as the only landing on the surface of Venus, but we'll come back to that. Venera had a rough start. The first probe didn't actually carry the Venera name. Much like with Mars and other programs, the Soviets would often give special designations to probes that failed to meet their mission goals. The first probe, launched on February 4, 1961, was called Tyazoly Sputnik, meaning heavy satellite, but only after the fact. To cover for the failure, the USSR declared the probe to be a test platform for future heavy satellites, though they had intended on launching it to Venus and impacting it into the surface. However, the probe failed after reaching orbit when the upper stage of its Molniya rocket was intended to reignite for an injection burn. Cavitation in the LOX pump, basically air bubbles caused by low pressure on the trailing sides of the flow, caused the pump to fail, which meant that the injection burn ended after 0.8 seconds when the engine shut down. Later that month, the probe fell out of its parking orbit over Siberia and disintegrated. Unfortunately, there are no photos or even artist concepts of the craft, but we do have this description from the memoirs of Boris Chertok, former Soviet engineer. Quote, "A pendant shaped like a small globe with the continents etched onto it was placed on the 1VA. Inside this small sphere was a medal depicting the Earth to Venus flight path. On the other side of the medal was the emblem of the Soviet Union. The pendant was placed in a spherical capsule with thermal shielding to protect it during entry into Venus's atmosphere at re-entry velocity." The second attempt was officially named Venera 1, and if you saw my Mars video, this design probably looks pretty familiar. Venera and Mars used, effectively, the same core design. A 3'5" cylinder topped with a dome which had 2 solar panels on either side, a parabolic wire mesh antenna, a shorter antenna boom intended for near-Earth communication, and an array of instruments designed to measure the solar wind, radiation, and others that aren't fully known. During its cruise in deep space, it used 2 trackers, one for the Sun and one for the star Canopus, to keep its attitude steady. However, just a week into its journey, the spacecraft failed to provide a telemetry check. Believed to be related to an overheated solar direction sensor, Venera 1 was effectively dead when it flew past Venus as intended in May of 1961, as it was incapable of returning any data gathered. Now, don't worry, the string of Soviet failures and eventual successes is far from over, but first we're going to hop across the ocean. NASA's Mariner program was dedicated to exploring both of Earth's nearest neighbors, but ended up focusing more on Mars in its back half. The first 2 missions, however, were intended to explore Venus. Designed by the Jet Propulsion Laboratory, NASA's R&D facility in California, Mariner 1 and 2 were identical probes adapted from the Ranger probes used to explore the Moon. However, this design was not by choice. The original choice was a more purpose-built original design, but this needed to be lofted with the high-energy Centaur upper stage, and Centaur simply wasn't ready in time. As a result, the Ranger-derived design was adopted to allow Mariner to launch on an Atlas Agena rocket. Mariner 1 had similar instrumentation to Venera 1. It was intended to measure solar winds, ion particles in deep space, cosmic radiation, as well as having some tools to measure the magnetic fields of Venus itself, as well as the temperature and electromagnetic radiation. There was a bit of a rush to get it and its sister spacecraft on the pad. There was only SLC-12 available for the rockets, which took a minimum of 24 days to prepare. The probes were intended to arrive at Venus within 9 days of each other, and had to launch within a 30-day period, itself a very specific window of opportunity. There was very little room for error. Mariner 1 launched after a full day of delays on July 22, 1962. Almost immediately, the rocket began to drift northeast, off of its planned trajectory. Mission Control attempted to correct for this drift, but the Agena booster continued to drift further, its trajectory moving perilously close to shipping lanes and inhabited areas. Just before stage separation, Range Safety sent the command to destroy the booster, and therefore the payload, which fell harmlessly into the ocean downrange. JPL engineers spent 5 days analyzing the flight data, determining the failure to be linked to both an error in the guidance computer and a hardware failure. In short, the guidance computer lost its connection to the ground systems briefly, and when it was re-established, it believed itself to be off course even though it wasn't, and tried to correct for it, which actually took it off course. Contrary to popular belief, this was not the result of a missing hyphen in the flight software, though there was a component of a symbol missing that contributed to the failure. Mariner 1's failure was one of many things that contributed to the developing field of software engineering, making many realize how important such a discipline was going to be in the future of spaceflight. Just 2 days before the second Mariner spacecraft took flight, the Soviets would make another attempt at the Venera program, though again it wouldn't carry the Venera name. Officially designated 2MV-1 No. 1, this was the first attempt in the program to create a lander for Venus, though its details remain shrouded in Soviet secrecy. Not that it matters very much, as this Molniya carrier rocket failed after reaching low orbit. Before performing its injection burn, the upper stage fired its Ullage motors, used to push the fuel toward the back of the tanks and prevent the engine from starving. However, one of these Ullage motors failed to ignite, and upon engine ignition, the entire stage quickly tumbled out of control and the engine cut off 45 seconds later. The vehicle never left Earth orbit and crashed back into the atmosphere only 3 days after launch. Mariner 2, the fifth attempt at a Venus spacecraft, would be the first success. Launched on August 27, 1962, you may think it would have been delayed until the fix for Mariner 1's failure had been implemented, but the software bug had not yet been identified and the window to launch was closing. However, this time the Atlas Agena maintained connection with the ground systems and the launch went entirely according to plan. Mostly. Shortly after shutdown of the Agena booster engine, one of the vernier engines lost pitch and yaw control, causing it to bang against its stops and roll the vehicle. The roll kept mission control from maintaining a downlink and sending any corrective commands, but the rolling stopped at T plus 189 seconds and the launch finished without any further incidents. Interestingly, the issue with the vernier engine had been caused by a loose electrical connection, and the rolling actually pushed it back into place and solved it. Mariner 2's trip to Venus wasn't very smooth. 13 days after launch on September 8th, the probe lost attitude control, and the science experiments designed for its cruise phase were switched off. Before the exact nature of the problem could be ascertained, it promptly returned to normal. A popular theory for the cause was that Mariner 2 had been struck by a small object, knocking it into a position that caused it to lose lock on the sun. However, this seems somewhat unlikely, as the problem happened again on September 29th and was again resolved before it could be properly analyzed. On October 31st, one of the probe's solar panels very suddenly deteriorated, believed to be related to a short circuit. Just in case, the science instruments were again switched off to conserve power, but the panel suddenly resumed normal activity a week later. Then on November 15th, the panel failed entirely. However, by now, Mariner 2 was close enough to the sun that one solar panel provided adequate power, allowing it to leave its instruments active as it approached Venus. On December 14, 1962, Mariner 2 became the first spacecraft to successfully perform a flyby of another planet, passing within 34,000 kilometers of the surface of Venus. Its instruments confirmed the temperature of the atmosphere to be in the range of 500 degrees Celsius or 932 degrees Fahrenheit, and it used 3 microwave radiometer scans of the planet to determine this, one over the dark side, one near the terminator line, and one over the day side, which helped to determine that there was little temperature difference on Venus based on the time of day. A large amount of the data related more to studying interplanetary space on the way to Venus, confirming things like the continuous flow of solar winds, the density of cosmic dust becoming lower further away from the Earth, and the value of the astronomical unit, which was at the time the distance between the Earth and the Sun, but has since changed to a fixed value. Mariner 2 also contributed to research confirming Venus's slow rotation speed, as well as estimates of its mass. Alright, are we ready for a very, very lengthy string of Soviet failures? Move fast and break stuff indeed. I have no idea what I'm going to use for reference material here while I'm editing, because there's no photos or videos of any of this. Venera 2MV-1 No. 2 launched just a few days after Mariner 2, but the ignition command for the upper stage never reached it, leaving the fuel valves closed and the probe stranded in Leo, where it re-entered the atmosphere a few days later. 2MV-2 No. 1, presumably a new generation of Venera craft, launched just 11 days afterwards. After reaching orbit, one of the oxidizer valves failed to close, causing liquid oxygen to spill into the combustion chamber of one of its vernier thrusters, which exploded, causing the entire upper stage to tumble. The tumbling starved the upper stage oxidizer pump and the engine failed less than 1 second after relight. It re-entered the atmosphere on September 12, 1962. In February of the next year, 3MV-1 No. 2 launched, but liquid oxygen leaked into a kerosene fuel duct due to a faulty valve during ascent, causing the entire middle of the rocket to explode during stage separation. The remains crashed 52 miles or 85 kilometers north of a small town in Siberia. Next was Cosmos 27, a common designation that Soviets gave to failed launches, though it is believed this was, like the previous attempt, a third-generation deep space probe. It launched in March of 1964, but after reaching orbit, a circuitry failure resulted in complete loss of attitude control, making it unable to perform an injection burn. It re-entered the atmosphere the next day. The next launch was not a Venera launch, but a Zond, Zond 1. This program was divided into 2 parts. One was a series of test spacecraft for robotic circumlunar flights, and the other was a series of interplanetary probes. Obviously, Zond 1 was the latter, and was the first to be launched after the Molniya rocket had finally resolved its serious ullage motor problems. This time, the entire launch sequence went perfectly, and Zond 1 was sent on its way to Venus. However, during the cruise phase, the electronics compartment began to slowly lose pressure, a big problem for a probe relying on vacuum tubes. A sensor window had cracked, and without a carefully controlled environment, the electronics would begin to overheat. Worse, a command was sent from ground control to turn on its radio system, and with the thin atmosphere inside the electronics compartment, there was an electrical discharge that effectively fried the entire system. Zond 1 was dead, and chief designer Sergei Korolyov was so upset about it that he demanded OKB-1, the corporation responsible for Soviet spacecraft design and manufacturing, begin using X-ray tests for quality control to check for pressure leaks. Venera 2, though obviously not the actual second Venera mission, launched in November of 1965. Again, the launch and injection phases went fine, and this time it even made it all the way to Venus without issue. The way the craft operated required its communications equipment to be switched off when its scientific instruments were activated, and after it gathered its data, the communications would be switched back on. However, they never did switch back on. Venera 2 operated completely according to plan right up until the point it was supposed to send back data, and then just stopped talking back. After analyzing all of the data it had been sending, controllers came to the conclusion that Venera 2 had overheated. 40 different thermal radiator elements had failed, causing a sharp increase of gas temperatures within the spacecraft. This caused elements of the receiving and decoding units to fail, making it unable to continue transmitting back. Venera 3 was up next, launching only 4 days after Venera 2. Around this time, OKB-1 was about to lose control of the Venera program, as the Soviet Central Committee had grown frustrated with the long string of failures. Control was being handed over to the Lavochkin Bureau. Lavochkin began an intense testing program of the Venera probes, immediately uncovering several design flaws, among these being that most of them failed when subjected to only half of the G-forces they were designed to withstand. However, OKB-1 still had 2 more finished probes ready to go, the first of which was Venera 3. Launch and injection were nominal. Molniya was basically a solid functional rocket at this point, but a month before it was scheduled to reach and impact Venus, contact was lost. Venera 3 was dead again due to overheating problems. Though it did technically become the first spacecraft to impact another planet, it was just inoperable when it did so. One begins to see why so many accusatory eyes were being set on OKB-1. Just what were those guys doing with these probes? The final OKB-1 Venus mission was designated Cosmos 96. You know what that means, right? Means it didn't go well. Into its third stage flight, a fuel line rupture caused an explosion in the engine and a loss of control. Somehow it still made it into orbit, but the explosion had made the fourth stage unable to ignite, so it was stuck there, re-entering the atmosphere of December 1965. It was seen as a fireball streaking through the sky over Ontario, Canada, sparking numerous UFO sightings. OKB-1 was out, and Lavochkin was now in. Would it surprise you to learn that this new bureau was going to succeed on its very first attempt? Venera 4 launched in June of 1967. While technically a prototype lander, it wasn't designed to operate on the surface, but rather enter the atmosphere and fall through it while returning data before impact. It was far more robust than previous probes, having undergone strenuous stress testing and using an improved gas-based cooling system rather than the liquid cooling used before. The lander portion contained an altimeter, thermometer, barometer, hydrometer, and gas analysis instruments. It was even designed to float in the case of a water landing, since the nature of the surface of Venus was a complete unknown. Of course, this did make a bold assumption that whatever liquid it landed in would be the same density as an ocean or lake on Earth. Venera 4's launch and injection went nominally, and it reached Venus in October of 1967. The lander separated, with the orbiter acting as a relay, and entered the Venusian atmosphere, aiming for a landing site at 19 degrees north and 38 degrees east. The descent was rough. The heat shield reached temperatures of 11,000 degrees Celsius or 19,800 degrees Fahrenheit, right at the limit of what it was designed to take. The cabin of the capsule reached a peak of 300 Gs of acceleration during its 93-minute parachute-assisted descent. Unlike Mars, parachutes work exceptionally well on Venus, the dense atmosphere allowing objects to fall much more slowly with much smaller parachute surfaces. The chute deployed at 52 kilometers or 16 miles from the surface, and the probe began to return data. The atmospheric pressure worked its way up from 1 standard atmosphere all the way to 22 atmospheres, and the air temperature rose to 262 degrees Celsius and 504 degrees Fahrenheit. The composition of the atmosphere was measured to be mostly carbon dioxide, between 90 and 93%, with a small amount of nitrogen, an even smaller amount of oxygen, and water vapor. The results of Venera 4 led to several corrections about the details of Venus, including its magnetic field being 3,000 times weaker and the hydrogen corona being 1,000 times less dense. There was no atomic oxygen, and if there ever was water, it had left the planet a long time ago. The first successful Soviet Venus mission was complete, and things will begin to look up from here. Returning to the Mariner program, the fifth probe in this program would be the second to last devoted to Venus, with all the others being sent to Mars, save for one. After Mariner 4 was such a success, Mariner 5 was then modified to explore Venus. The changes were fairly minor. Since the spacecraft would be facing the other way to maintain its connection with Earth, its solar arrays were flipped 180 degrees to face the Sun. In addition, the high-gain antenna had to be mounted at a slightly different angle, and a deployable sunshade was included for extra thermal control. Mariner 5 lifted off on June 14, 1967, 2 days after Venera 4, on an Atlas Agena. The vehicle reached orbit successfully, and although there were fluctuations in engine chamber pressure during the injection burn, it was still sent successfully toward Venus. This anomaly did, however, preclude a redesign of the Agena's turbopumps to correct for it in the future. The flyby occurred in October of the same year, coming within 3,990 kilometers of the surface. Its further refined instruments found that, despite lacking a magnetic field, the incredibly dense ionosphere creates a kind of bow shock effect that deflects solar winds around the planet. Like Venera 4, it also found a hydrogen corona, but no atomic oxygen. Its analysis of the atmosphere density greatly contrasted that of Venera 4, not 22 atmospheres of pressure, but 75 to 100, indicating a possible faulty instrument on Venera 4. However, a conference at Kitt Peak National Observatory the next year, one of the first major meetings to discuss interplanetary exploration between two nations, concluded that neither spacecraft had been entirely successful in communicating data about the surface conditions of Venus. Just 3 days after Mariner 5's launch, the Soviets continued with their Venera program with the launch of Cosmos 167. We remember what Cosmos means, right? Intended to be a Venus lander, this probe was stranded in low orbit when the upper stage simply failed to ignite. The engine had not been properly cooled prior to ignition, and the upper stage and probe never left low orbit, re-entering the atmosphere a week after launch on June 25, 1967. Venera 5 and 6 were launched in January of 1969, similar in design and intention to Venera 4, though more robust. Intended to enter the atmosphere and study it on the way down, they were launched on the 5th and 10th respectively, both reaching orbit and performing injection burns without issue. One thing I haven't really mentioned yet because it lacks any scientific value is that virtually all of the Venera landers held some manner of propaganda or memorabilia. Usually these were coins or flags bearing Soviet emblems, though Venera 5 and 6 both had a Soviet medallion and a bas-relief of Vladimir Lenin. Considering mass constraints, I wonder what else was cut from the landers so that they could have a rock with Lenin's face on it. Upon Venus approach, the landing capsules were ejected and headed toward the planet. They both deployed parachutes, made deliberately smaller this time now that the density of the atmosphere was more well known, and descended for 53 and 51 minutes respectively. Unfortunately, there isn't a whole lot of information on exactly what data was obtained, though it was likely simply further refinements of the results of Venera 4, given the contradictory information received by Mariner 5. It is known that the data provided more refined mass estimates for the planet, and UV photometers made the same observations of a hydrogen corona, but no atomic oxygen. Water concentrations were found to indicate that part of the atmosphere would not be saturated enough to form water clouds. Some photometers registered 25 watts per square centimeter, and it wasn't confirmed whether or not these were simply instrument errors or the presence of lightning within the clouds. Both landers went silent at an altitude of around 18 kilometers, likely crushed by the increasing atmospheric pressure. Following the success of this pair, it was time to continue past the atmosphere. It was time to land and take readings from the surface. From this point, I'm going to attempt to streamline the Venera program somewhat. Unlike Mars, there isn't a whole lot of options for exploring Venus. You can't really do long-duration landers or rovers without incurring a massive weight and therefore a massive cost penalty, so the program gets a little samey from here. Not to mention, at this point in history, lift capabilities are limited. The Soviets have the R7, or the R7, or the R7, or the Proton, which at this point is not particularly reliable. The vast majority of landers are fairly identical with small changes here and there, so we'll be focusing on those changes as well as any new findings rather than doing a straightforward breakdown of each and every mission. Venera 7, for instance, the first lander, is largely identical to the previous atmospheric capsules, though made more robust to survive all the way down to the surface. In fact, it was made so robust that there was very little left over for scientific instruments, my previously mentioned problem that limits exploration of Venus. The lander was designed to withstand up to 18 megapascals or over 170 Earth atmospheres and temperatures of 580 degrees Celsius or 1076 degrees Fahrenheit. Visually, the design was similar to previous capsules, being roughly spherical with instruments and parachutes on top. Launch and arrival at Venus went according to plan, and it entered the atmosphere and began transmitting data during parachute descent. However, 6 minutes into that descent, the parachute ripped and the probe free fell to the surface. It impacted at about 17 meters per second or 48 miles an hour and apparently rolled onto its side. Upon touchdown, its signal weakened, returned to full strength, then all but disappeared. Initially believed to be dead on arrival, Venera 7 actually continued transmitting a very weak signal for about 23 minutes, the roll causing its high-gain antenna to be in an improper orientation. In terms of raw results, it did little more than confirm what was already suspected. Surface temperatures and pressures made it completely inhospitable, and there was zero possibility of liquid water on the surface. It also recorded wind speeds of up to 2.5 meters per second or 5.6 miles per hour. It was not an ideal mission, but certainly admirable for a first attempt. After another Cosmos failure, an electrical problem shut down the upper stage engine 25 seconds into the injection burn, Venera 8 became the first wholly successful landing in 1972. Nearly identical to Venera 7, this time the parachute operated normally and the probe touched down successfully, operating for 63 minutes before succumbing to the harsh environment. It confirmed the previous measurements of Venera 7, indicating its partial failure didn't compromise any of the instruments, but also evaluated the ambient light levels, showing them to be sufficient for surface photography and similar to an overcast Earth day with about 1 kilometer of visibility. Venera 8 also made the first measurements of the surface regolith, finding its composition to be similar to alkali basalt, a form of volcanic rock. A profile of the cloud layer was also obtained, detecting sulfuric acid within them. Another Cosmos failure later, this one separated into 4 pieces and fell over New Zealand, briefly igniting an international controversy when the USSR denied ownership of it, Mariner 10 was up to bat, the final spacecraft in the Mariner program. It was intended to explore both Venus and Mercury, but because it wasn't simply passing by Venus on the way to Mercury, it makes the list. It did, however, incorporate its Venus flyby as a gravity assist measure to more easily reach Mercury. Launched in 1973, it made its closest approach to Venus in the next year after a cruise phase fraught with technical malfunctions that required constant maintenance and corrections. The computer kept resetting itself, the star tracker kept locking onto a flake of loose paint, and the power system kept short-circuiting. It seemed as if we were always just patching Mariner 10 together long enough to get it onto the next phase and the next crisis, said Donna Shirley of JPL. Mariner 10 passed within 5,768 kilometers of the planet, becoming the first spacecraft to return images of the planet both in real colors and ultraviolet. The prior lacked much detail as the cloud cover is virtually featureless, but the ultraviolet images revealed more detail of the different layers of clouds and how they moved. Additionally, the gravity assist maneuver was also wholly successful, allowing Mariner 10 to head beyond Venus and become the first spacecraft to visit Mercury, flying past it once, then looping around the Sun to fly by it a second, then third time. Venera 9 and 10 were the beginning of a complete redesign of the existing program, intending to operate longer on the surface of Venus and return more valuable data. The spherical shape was expanded into the more well-known configuration I refer to as the ball-with-hat lander, with a ring at the bottom that supported landing with a suspension system, and the hat, the large ring at the top, was used to provide friction against the air after it was separated from its parachute, slowing its descent before touchdown. The entire thing was encased in a spherical shell during re-entry, and explosive bolts would separate it once it was ready to deploy parachutes. The beefed-up lander design, as well as the probe portion now being orbital rather than for flyby, required a new, heavier carrier rocket, the Proton K heavy lift vehicle. Venera 9 landed on a steep slope on the surface of Venus on October 22, 1975, while its carrier probe burned retrograde to become the first spacecraft to orbit Venus. Being the first lander to carry a camera, Venera 9 returned the first ever images from the surface of Venus showing a cloudy skyline and jagged rocks on a relatively smooth surface. Over the next 53 minutes, Venera 9 would gather and transmit as much data as it could before the extreme conditions finally took it offline. The light levels were recorded at 14,000 lux, similar to Earth in full daylight but without any direct sunlight. Clouds were measured to be 30 to 40 kilometers thick with bases at around 35 kilometers in altitude. Atmospheric chemicals measured included hydrochloric acid, hydrofluoric acid, bromine, and iodine. The surface pressure was found to be around 9,100 kilopascals, or about 90 atmospheres. The temperature was around 485 degrees Celsius or 905 degrees Fahrenheit. Because there was no direct sunlight, there were no shadows in any images, and there was no dust in the air. The intention had been to take 360-degree panoramic photos, however one of the camera lens caps failed to come off, leaving the lander with half of the desired view. These lens caps would continue to be an issue that plagued the rest of the Venera program. Venera 10 landed approximately 2,200 kilometers away from and 3 days after its predecessor. and also had a repeated failure of one of its camera lens caps, only able to provide 180-degree views. This location showed less of the jagged surface rocks and more flat pancake-like slabs covered in a fine-grained material closely resembling areas on Earth that surround volcanoes. At this time, it was strongly believed that Venus had once hosted intense volcanic activity, but this was in its distant past. Venera 10 operated for 65 minutes and may have actually remained active longer, as it stopped transmitting only because the orbiter had moved out of range, but was inoperable by the time it came back around. In September of 1978, Venera 11 and 12 were launched. Fairly similar to the previous two, these landers had a few new instruments to do analysis of the planet, including a penetrometer intended to be pushed into the soil and confirm its composition, as well as a microphone to record audio. Both had stripped-down parachute systems to make room for more experiments, and the parachutes were jettisoned at 49 kilometers at the bottom of the cloud layer. Venera 12 threw up a cloud of dust when it touched down, darkening the sky for 20 to 30 seconds, but Venera 11 curiously didn't. Both allowed for more detailed analysis of trace gases, finding chlorine to be 10 times more common than sulfur, leading to a conclusion that the clouds contained a non-volatile chlorine compound. An experiment called GROZA, designed to detect emissions from lightning, found bursts of low-frequency radio noise consistent with lightning storms on Earth, but significantly more intense. Some speculated that because they occurred low in the atmosphere, they were similar to lightning storms found around intense volcanic activity on Earth. The activity was also much lower near Venera 12 compared to 11, indicating they were possibly localized events. Unfortunately, both landers experienced several instrument failures. The microphones weren't able to record, none of the camera lens caps deployed, and the penetrometers also failed, possibly due to a hard landing. It was believed that the extra instruments had caused oscillations during descent, and pressure equalization hadn't occurred, the intense forces on the surface preventing the caps from deploying. In the same year as this latest pair of Venera landers, the United States returned to Venus with the Pioneer Venus program. It was launched in two segments. Pioneer Venus 1 contained an orbiter, intending both to gather data from afar and act as a relay for the second portion of the mission. Pioneer Venus 2 was also known as the Pioneer Venus multiprobe, containing one large and three smaller probes intended to enter the atmosphere and study Venus during its descent. The orbiter was launched in May 1978 aboard an Atlas Centaur, arriving at Venus in December. Manufactured by Hughes Aircraft, the orbiter consisted of a simple cylindrical bus with a solar panel wrapped around the outside and a propulsion on one side of the cylinder and instrumentation on the other. Orbit insertion was achieved via a Star 24 solid rocket motor, the low end of the orbit being 200 kilometers from the surface and the high end over 66,000 kilometers, allowing for a 24-hour orbital period and a long period of time to transmit back data obtained. After some initial measurements, the periapsis was raised and operation continued all the way until 1992. Pioneer Venus was the first spacecraft to produce a near-complete map of Venus from radar data, and in addition to lengthy examinations of the atmosphere and cloud layers, was also able to analyze Halley's Comet while it was unobservable from Earth. Similarly designed by Hughes Aircraft, the multi-probe bus was also a cylinder with the four probes located on top. The bus was designed to enter the atmosphere after deploying the probes, measuring the atmosphere with two spectrometers. It lacked a heat shield and parachutes designed to continue transmitting until destroyed by atmospheric forces, which occurred at an altitude of around 110 kilometers. The four probes were similarly not designed to survive landing, with only the larger probe carrying a parachute intending to detach near the ground. The large probe carried more experiments, the parachute allowing the instruments to function longer than the three small probes. These, the North Probe, the Night Probe, and the Day Probe, were deployed to land at different parts of the planet corresponding to their names. They entered the atmosphere over an 11-minute period, with the large probe first. The results of all probes were nearly identical once they reached below 50 kilometers in altitude, identifying three distinctive cloud types, a much higher ratio of argon in the air than on Earth, and confirming various pieces of data from previous Venera missions. Each probe impacted the surface as planned, and their downlink was lost. First the large probe, then the North Probe, then the Day Probe, then the Night Probe. However, then something remarkable happened. The Day Probe continued to transmit. Operating for 67 minutes and 37 seconds after impact, the Day Probe unintentionally made the United States the second country to land on Venus, though since it wasn't the intention, it often isn't remembered as such. But as far as I'm concerned, it still counts. The two final batteries of Venera missions would include a few very interesting firsts. Venera 13 recorded the first audio from the surface of Venus, with its microphone being turned on in the last stages of its descent. We can hear the sounds of Venusian wind, a dull thud as the lander impacts the surface, and a second thud as the camera lenses are blown off with small explosives. These cameras produce the first color images of Venus, showing how truly alien and hostile the planet looks. This also resulted in a moment of confusion among some researchers. 3 members of the Space Research Institute and the Russian Academy of Sciences suggested that signs of life existed in the images, publishing articles pointing to certain disc-shaped objects visible near the lander and stating that they moved between images. However, engineers familiar with the lander were quick to point out that these were the pieces of the blown-off lens caps. The illusion of movement was caused by looking at 2 photos on either side of the lander and therefore showing 2 different lens caps in different locations. I don't know how they didn't realize this, since the entire terrain around the lens caps also changed between images. Venera 14 repeated the feats of the previous, providing new color panoramas as well as reinforcing that the previous objects were in fact lens caps. However, these lens caps had a new problem. Let's take a quick listen to the slightly better quality audio provided by this lander. You hear that sound at the end? Sounds like drilling, right? Well, it is. That's the sound of Venera 14 attempting to drill into the surface of Venus. However, one of the lens caps had fallen directly onto the spot that it was intended to drill. The probe was actually attempting to drill into the metal cap and was obviously unsuccessful. Venera 15 and 16, the final missions, consisted of only orbiters, no landers. They entered into near-polar orbits around Venus, enabling them to map the missing parts of Venus from the Pioneer Venus mission. They covered approximately 25% of the planet over an 8-month mapping operation. Despite the Venera program being over, the next missions to visit Venus would come again from the USSR and occur in the very next year, 1984. The Vega program launched 2 spacecraft in December of 1984 and were to fly by Venus, deploy atmospheric probes, and then use it for a gravity assist to approach Halley's Comet and also study that. The spacecraft both contained a lander as well as a unique atmospheric probe, being a balloon. Venus is uniquely suited for balloon-based craft, as the composition and density of its atmosphere allow a variety of gases to be used. On Earth, only hydrogen and helium work as lifting gases, but on Venus, both oxygen and nitrogen can work effectively. Vega 1 and 2 were the first to test this concept, with the balloons being contained inside the lander modules. The landers themselves were virtually identical to the last series of Venera landers, with the balloons held up top. After atmospheric entry, a top cap was opened and the balloon was pulled out of its compartment by the parachute at about 63 kilometers. At 54 kilometers, the balloon was inflated with helium and the parachute and inflation system were jettisoned. 3.4 meters in diameter with a gondola of instruments suspended 13 meters below it, the balloon was made of a Teflon cloth matrix coated in Teflon and filled to 30 millibars over pressure. It achieved a stable height around 54 kilometers in the most active layer of the Venusian clouds. Both balloons drifted westward from there, taking steady measurements and crossing the terminator line from night to day. They would each travel around 11,000 kilometers through the atmosphere before their instruments failed, though the balloons themselves likely stayed inflated much longer. Finally, the year is 1989 and the United States returns to Venus with the Magellan probe. The product of plans dating back to 1970s radar mapping plans, Magellan was the first interplanetary probe to be launched by the Space Shuttle, the first to use the inertial upper stage booster to reach its destination, and the first spacecraft to use aerobraking to circularize its orbit. If you're unfamiliar or you missed the Mars video, let's just go ahead and plug that one again. Aerobraking involves lowering the periapsis of an orbit into the atmosphere of a planet, which will cause it to slow down until it rises back up into space, slowly lowering its apoapsis until its orbit is roughly circular. This method saves significant amounts of fuel, as the spacecraft can significantly alter its orbit while spending a very minimal amount of fuel to lower and raise the periapsis. It isn't without its risks. One Mars mission had a solar panel bent backwards by atmospheric forces, but Magellan was intended to prove that the concept works. The initial plan called for a very simplistic spacecraft called the Venus Orbiting Imaging Radar Project, but in 1985 was renamed Magellan in honor of Portuguese explorer Ferdinand Magellan. Magellan had 4 specific objectives: obtain near-global radar images of Venus with resolution equivalent to optical imaging, obtain a topographical map of the same, obtain near-global gravity field data, and develop an understanding of the planet's geological structure. Designed and built by Martin Marietta and JPL, Magellan consisted primarily of spare parts as a cost-saving measure. Her attitude control computer was a spare from the Galileo probe. Its main bus was a spare Voyager probe bus, its medium-gain antenna was a spare from Mariner 9, and so forth. Even its propellant tank was made out of a Space Shuttle Auxiliary Power Unit. Magellan launched on May 4, 1989 aboard Space Shuttle Atlantis on STS-30. Once in orbit, the probe was deployed from Atlantis on the next day, its inertial upper stage sending it toward Venus.
Once we elevated up to 29 degrees and then on up to 52 degrees for the deploy, we went ahead and threw the switch and sent Magellan on its way. It comes out of the payload bay at about half a foot per second, and during the first minute we just sit there and watch it leave the orbiter bay. We're in free drift as far as the shuttle is concerned, and the way it is deployed, as you know, is a super zip. It's a mechanical or a metal band around the IUS that is separated, and several springs send it from the payload bay. And this is when the solar arrays deployed. They deployed 10 minutes after the IUS was deployed in connection with the RCS system on IUS being activated. And this is a nice shot we got. We initially thought that Venus was going to be too close to the sun for us to even see, but we didn't realize till we got up there and followed it several times after sunset. We could see Venus trailing the sun at the terminator. So we got a picture of Venus sunset, and down in the lower portion you see some of the clouds, that thunderheads that had built up.
It reached Venus 15 months later on August 10, 1990. The original plan had been much faster, utilizing the more powerful liquid-fueled Centaur upper stage, a method that was abandoned following the Challenger disaster. The lower-powered solid-fueled IUS created a much slower, but effective, mission profile. Magellan entered a highly elliptical orbit of Venus of 295 kilometers or 183 miles by 7,602 kilometers or 4,823 miles. This allowed it to map the surface during low passes while transmitting data back during the higher phase of orbit. By May of 1991, 83.7% of the surface had been mapped. The mission was extended to gather data on the gaps, and by January of 1992, 96% of the surface had been mapped. At this point, the mission was extended a third time to gather stereo imagery of the surface that would allow for the construction of detailed three-dimensional renderings of the surface, as well as increasing coverage to 98%. By the fifth mapping cycle in 1994, Magellan began acquiring high-resolution gravimetric data, as well as performing the first aerobraking maneuvers to lower its apoapsis. Following the sixth and final mapping cycle, Magellan performed its last experiment, the windmill. It entered the atmosphere with its solar panels perpendicular to the air, while the thrusters fired to keep it from spinning. This provided valuable data on oxygen-gas surface interactions, which would be used to design future satellites as well as plan for future aerobraking maneuvers. Following this, the probe fully entered the atmosphere and disintegrated on October 13, 1994. The results of Magellan's mapping projects have been studied extensively since the end of its mission. It has helped to determine that there are relatively few impact craters on the surface of Venus, suggesting its surface to be less than 800 million years old, that it is covered in volcanic materials, has typical signs of plate tectonics, and very little material has been transported by surface winds, unlike Mars. Just last year, in 2023, analysis of Magellan data showed that not only did Venus used to be highly volcanic, it still is. From here on out, remaining Venus missions were conducted by new nations. In 2005, ESA launched Venus Express aboard a Soyuz carrier rocket. Initially proposed as a counterpart to their Mars Express mission, the nature of reaching and orbiting Venus required significant redesign work of the spacecraft, including enhanced protection against radiant heating and ionizing radiation. However, at the same time, its solar array system would be able to generate much more energy around Venus given the proximity to the Sun. The spacecraft had two primary missions. The first was to analyze the climate of Venus, and the other was to use Earth as a way to enhance exoplanet research. From Venus, Earth is less than 1 pixel in size, which mimics Earth-sized planets seen in other planetary systems. By searching for signs of life on Earth from such a distance, researchers could enhance methods of searching for life on exoplanets. Venus Express entered Venus orbit on April 11, 2006. By the end of the year, it had obtained a complete temperature map for the surface of the planet, and its mission was extended 5 separate times. It would later find evidence of past oceans, a layer of ozone in the upper atmosphere, a much higher prevalence of lightning than on Earth, and discover a huge atmospheric vortex at the South Pole. After 8 years in orbit, with propellant to maintain orbit running low, the mission was officially concluded on May 15, 2024. Back in May of 2010, JAXA entered the Venusian ring. Akatsuki, meaning dawn, was launched aboard an H-2A rocket and performed a little bit of a miracle. The first interplanetary probe from JAXA since the failed Nozomi in 1998, Akatsuki was intended to study Venus in multiple wavelengths, including looking for evidence of lightning in the visible spectrum, analyzing Venusian meteorology, and attempt to decipher the reason for the planet's incredibly fast atmospheric rotation. While the planet itself rotates at around 6 km per hour, the atmosphere rotates at an astonishing 300 km an hour, and the process by which it does so is not entirely known. Upon arrival at Venus, Akatsuki initiated its orbit maneuver with a planned communications blackout while the planet passed between the probe and the Earth. However, when it re-emerged, it was in a safe mode and it wasn't in orbit. It was quickly determined that its engine had shut down early, with a likely explanation that salt was jamming some valves. The combustion had become oxygen-rich and the engine was virtually unusable. As the probe was flung into heliocentric orbit, a plan was made to try again when Venus came back around in late 2015. Remaining oxidizer was vented to reduce weight, and upon approach to Venus, it executed a 20-minute burn using hydrazine reaction control thrusters. These thrusters are meant for attitude control, to perform small course adjustments, and it's genuinely impressive that they worked for such a sustained burn, successfully placing the craft into orbit. Better late than never. Over the next 8 years, Akatsuki gathered a remarkable amount of data, observing a bow-shaped feature in the atmosphere deemed a gravity wave, revealing something similar to jet streams occurring in the low and middle cloud regions, and producing 3D maps of the Venusian atmospheric structure. Its goal of imaging visible lightning has been unsuccessful, despite being able to see the dark side of Venus for 30 minutes every day. This likely indicates that lightning only occurs on Venus in lower cloud layers, out of sight from orbit. In April of 2024, the Akatsuki mission was declared complete, and the probe was taken offline the next month. Deployed alongside Akatsuki was Ikaros, standing for Interplanetary Kite Craft Accelerated by Radiation of the Sun. Intending to simply fly by Venus, Ikaros was the first spacecraft to successfully demonstrate solar sail technology, a concept speculated about for centuries, which utilizes solar winds to provide acceleration for the spacecraft without using any fuel. Carl Sagan would have been incredibly proud to finally see it happen. It had 4 specific technology demonstrations to perform. First, successfully deploy the sail. Second, demonstrate the use of film-thin solar cells integrated into the sail. Third, measure its acceleration due to radiation pressure on the sail. Fourth, vary the reflectance of its 80 liquid crystal panels to perform attitude control. All 4 of these experiments were successful by the end of 2010, and it successfully performed its flyby maneuver, continuing into orbit of the Sun and operating on and off until May of 2015. The latest mission to Venus, surprisingly enough, was not successful. Also launched in 2010 alongside Akatsuki, Shinen was a student spacecraft launched as a secondary payload. Its primary purpose was to test the robustness of 6 university computers against radiation and extreme temperatures. However, upon reaching orbit, contact was quickly lost and never re-established. The reason for the failure is, at this time, unknown. So what's next for Venus? As of right now, 7 individual missions are under development for the near future, with many more proposed. MIT and Rocket Lab are developing the Venus Life Finder, an atmospheric probe intended to search for organic compounds in the atmosphere. The CNSA, the Chinese space agency, are developing VOICE, standing for Venus Volcano Imaging and Climate Explorer. ISRO, India's space agency, is developing the Venus Orbiter mission, a successor to their very effective Mars Orbiter mission. Roscosmos is working on Venera D, though progress is excruciatingly slow due to the more or less stagnant nature of the Russian space program following the invasion of Ukraine. NASA are developing Veritas and Da Vinci, a combination orbiter and atmospheric probe, and let's just take a moment to appreciate JPL's absurd naming conventions. Veritas stands for Venus Emissivity, Radioscience, INSAR, Topography, and Spectroscopy. You can't have an acronym in an acronym, guys. Da Vinci stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging. I swear, JPL has an entire department dedicated to first figuring out an acronym, then figuring out which words will actually form that acronym. Veritas will build on the success of Magellan and focus on Venus's volcanic activity, while Da Vinci will attempt to understand the origins of the Venusian atmosphere. Lastly, we have Envision, an ESA probe to provide more refined, high-detail radar mapping of the planet. But what will follow that? I fear not much. Venus is simply too hostile of a world to do much long-term research on it, with orbital missions providing far more useful data than even the largest battery of Venera landers. Its balloon-friendly environment has led to several lofty proposals, such as floating outposts in the upper atmosphere, but these present just as many challenges, if not more, than Mars habitability. At some point, we'll have to choose which planet we want to dedicate the time, effort, money, and materials to, and the winner is most likely going to be Mars. However, perhaps one day we can have floating cities on Venus. One day, Star Wars may become reality. Cavitation in the LOX pump, basically air bubble. Inside this small sphere was a... an array of instruments designed to measure